I want to talk about prime representations in the HL category, and this H is for Hernandez and this L for Leclerc. And the focus of this talk is on classical decompositions of some objects in that category, which are called prime. So although you guys are all familiar with quantum affine algebras or classical Lie algebras, I want to fix some notation. So what I'm going to start with are quantum affine algebras. So first, I should maybe say it's a joint work with my student Leon Barth. Okay, so the quantum affine algebra, for that, I need a Lie algebra first. And the Lie algebra I'm going to start with is the SLN plus 1. And SLN plus 1 consists of n plus 1 by n plus 1 matrices, so that the trace of this matrix is 0. So if you sum up over the diagonal entries, you end up with the 0 entry. And this SLN plus 1, well, you know how to multiply matrices, so that this is an algebra, the matrix space. But you can define another bracket on it, it's known as the Lie bracket. And the Lie bracket of two matrices, A and B, is just given by A times B minus B times A. And luckily, the space of matrices is non-commutative, so that you get really most of the time non-zero matrices if you plug in SLN plus 1 matrices into the bracket. Okay, so this SLN plus 1 has a few very typical matrices, and the one I want to discuss are these Xij pluses. So the Xij plus, it has a 1 in column j plus 1 and row I. And obviously, it's a matrix in SLN plus 1 because all the diagonal entries, so now I hope you see it when I at least do this, are 0. So of course, the sum over the zeros is 0. So this is really a matrix in SLN plus 1. So whenever you have a plus, then you should also have a minus. And this minus is more or less the transpose of the matrix. You just put a 1 into row j plus 1 and column I. And you have these matrices for all I less or equal to j between 1 and n. Again, since the diagonal entries are 0, the sum is 0, so it's really a traceless matrix. And also, you have certain diagonal matrices in SLN plus 1, and for that, you have a 1 at position I, and you have a minus 1 at position j plus 1, j plus 1. And if you sum up over the diagonals, then again, the trace is 0. So this is a matrix in SLN plus 1. So what you should see from here is if you take the direct sum over all I and j, you end up with the upper triangular matrices. If you take the direct sum over all ij with the minuses, you end up with the lower triangular matrices. And if you take the direct sum over all ij's, hij's, you end up with the diagonal matrices in SLN plus 1. So what I've written here is a basis of SLN plus 1, which is compatible with the triangular decomposition of SLN plus 1 into upper, lower, and diagonal matrices. So the representation theory of SLN plus 1 is well understood. So, well, of course, it's always dangerous to say it's well understood because it depends on the point of view, how you view the representation theory. But in my opinion, it's well understood from the perspective that you know character formulas, dimension formulas, bases, and so on. And especially, you know how to parameterize these finite dimensional irreducible representations. Namely, there is a one-to-one correspondence between the irreducible finite dimensionals and this lattice Z plus n. And I want to denote the generators, so it's the monoid generated by the fundamental weights omega I. So for each such lambda, you have an irreducible finite dimensional representation. So if you don't like Lie algebras, then you can think of representation theory of associative algebras by just associating to G the universal enveloping algebra, which is basically determined by a universal property, which is exactly written in this diagram. Namely, when you have a Lie algebra map from, so categorically, this just means whenever you have a Lie algebra map from G to B, this is the same as the algebra maps from U of G to B. Okay, so whenever you have this arrow over here, then you can extend it to an arrow from U of G to B. And the thing is that the representation theory of G and U of G is the same. Okay. And this kind of construction is nothing special which works for SLN+1. It works for every Lie algebra. And the Lie algebras I want to discuss in this talk are the current algebra GT, and also the loop algebra GT plus minus. So instead of allowing complex entries into the matrix space SLN+1, you just plug in polynomials or Laurent polynomials, and then you can again construct the universal enveloping algebra of these algebras. And also, I want to discuss the quantum version of these universal enveloping algebras. So you put another variable q and view it as a deformation. Again, it's dangerous to define it as a deformation, but it's an algebra which has certain generators and relations. So for example, if you look at the classical one, so this uq of g, it's generated by ei's, fi's, and ki plus minus, so I between 1 and n, and certain relations, and the important ones, which do not show up, for example, for SL2, are the quantum Serre relations. Okay, so this is the classical quantum group, uq of g, but if you go to the quantum affine algebra or quantum loop algebra, then the generators can again be stated in this way. So just to distinguish between the xij plus minus, which I have introduced at the beginning, and the generators of the quantum loop algebra, I made a tilde over here. So again, it has generators, but now the relations, they look a little more complicated. So this is in the second realization of the quantum loop algebra. Okay, so now if you want to do the representation theory of the quantum affine algebra, this is not so well understood in the sense that except in special cases, you don't know, for example, character formulas, dimension formulas, or bases. This is something which is not known. However, there is the result of Chari and Presley that you can parameterize again the irreducible finite dimensional ones. But now the monoid is very big. Okay, so you just take the monoid, which is generated by omega IA. So you allow a second entry A, and this A is any rational function. So if you ignore A, you're back to the classical case. But if you allow any rational function, then you parameterize the irreducibles for the quantum affine algebra. And again, for any pi, you have the associated representation VQ of pi. Okay, so this is just the notation. So once you know how the irreducibles are parameterized, you can introduce the Hernandez-Leclerc category. So what is this Hernandez-Leclerc category in this language? So this Hernandez-Leclerc category for type A depends on a height function. And this height function is, well, it's a function from this index set 1 to n to the integers. And you want that the difference is 1. So you choose kappa of 1, and then kappa of 2 has already two choices. Either you take kappa of 1 plus 1, or you take kappa of 1 minus 1. Okay, so once you have fixed this height function, you can look at a certain subcategory of the category of all finite dimensional representations of the quantum affine algebra. Namely, you take all objects in that category such that when you look at the composition factors, so you can build the Jordan-Hölder series of this representation, then you want that the composition factors have a particular form. So they are all irreducible. Well, it's a Jordan-Hölder series, but you want to say that this pi is a product of these omega IAs where you allow particular A's. Well, and this depends on the height function. You take q to the power kappa of I, or q to the power kappa of I plus 2. Okay, so that is the category. And what turns out is that when you build this category, then the K0 of that category carries the structure of a cluster algebra of type A. So it's a monoidal categorification of a cluster algebra of type A. And this category is closed under tensor products. Okay, so when you look at the cluster variables in this cluster algebra, they correspond to the so-called prime irreducible modules. So, well, it's still in red. I haven't defined prime. And the frozen variables more or less correspond to the minimal affinizations, which are in type A just pullback of evaluation modules. And the aim of this talk is more or less to look at the prime irreducibles in that category and focus on the classical decompositions with respect to the Hopf algebra UQ of G. Yeah, so you can take these and restrict them to the Hopf subalgebra UQ of G and ask for the Schur expansion of these characters. And this is the main aim of this talk, to determine this Schur expansion. Okay. Now, how do we continue? So I want to explain what prime means. So everybody knows what a prime number is. A prime number is when you take a prime number and write it as a product of other numbers, then basically this decomposition is trivial. Okay, so then you call an object prime irreducible. So take any irreducible. So this is just, okay, it's not 100% correct, this definition, but let me state it in this way. So you say VQ of pi is prime whenever you can write it as a tensor product of other irreducibles, then this has to be a trivial decomposition. So there exists no non-trivial decomposition into tensor products. So now if you are used to the representation theory of classical Lie algebras, you would say, well, why isn't every representation prime? Because if you think of irreducible for G, for example, then when is it possible to write V of lambda as a product of other irreducibles, right? So this is almost never the case, but in quantumifying case, generically a tensor product of irreducibles remains irreducible. So this definition makes perfectly sense. So now there is one question here, namely, you can ask to which pi, okay, so for which pi is VQ pi prime in this Hernandez-Leclerc category? And this question can be asked, which I want to explain now. So first of all, the goal is to understand, whatever understand means, the prime irreducibles in this category for all height functions kappa. And to say for which pi this representation is prime, I have to introduce a quiver. So let K kappa, well, it's a quiver of type AN. So again, you just take the AN quiver with some particular orientation, and this orientation depends on this height function kappa. Okay, so you take the quiver with vertices 1 to n, and you draw an arrow from I to I plus 1, well, depending if kappa of I is less than kappa of I plus 1, or you draw it in the opposite direction. But basically, it's just the AN quiver with an orientation. Okay, and then there's the result of Hernandez and Leclerc. I think they stated it as a remark, but it turned out later that it's more involved than just a remark. And now it follows from a recent paper of Brito and Chari. Namely, VQ pi is a prime object in C kappa. So it cannot be decomposed or written as a tensor product in a non-trivial way if there exists an interval J such that pi is exactly of that form. So you take certain omega I q kappa of i's and certain omega I q kappa of I plus 2, where in the first case you run over the sinks. So maybe I take another color. In this second case, you run over the sources. So what do I mean by that? So you take your quiver q kappa, and then you take well, some kind of orientation, say 1, 2, 3, 4, and this is the orientation induced by kappa. And let's say you just take J to be the interval 1, 3. Well, you just ignore 4, and then you just look for the sinks and sources in this interval. So this is what I mean by J sink and J source. Or there's one exception, which corresponds to the frozen variables, namely when pi is exactly of that form, and this is a minimal affinization. So, for example, this is as a module for SLM plus 1 or UQ SLM plus 1. In this case, this is just 2 omega I. Okay, so For the frozen variables, one does really know how the structure is. So now I want to discuss the methods to study these representations. Okay, so we have the category of all finite dimensional representations. We know how the irreducibles are parameterized. And also we know that it's hard to study all of them. So it makes sense to look at subcategories. And Hernandez-Leclerc category is one subcategory, categorifying a cluster algebra. And there you can look at the simplest objects, which are the prime ones. And now what is the method to study these prime objects? Okay. So let me first explain the idea. So the idea is to start with a representation for the quantum loop algebra and to end up with a representation for the current algebra. And there is a way, which you probably all already know, to go from quantum loop to current. And this way is known as the graded limit. Okay, so first, you take the classical limit, so you go q equals to 1, so q goes to 1 limit, and this gives you a representation for the loop algebra. Okay, so I will explain. So this star I will explain, and this star, double star, I also want to explain. Okay, so there is a way to go to get rid of this q and to end up with a representation for the loop algebra. And then by restriction, so this is just restriction, you get a module for the current algebra. But this is a module which you don't want. Instead of taking the restriction, you go further by taking a pullback. Well, the polynomial algebra has an isomorphism where t goes to t minus 1, and you take the pullback of that isomorphism to end up with a representation which is called L of pi. Okay, so this is the way to go from quantum to classical and to get a graded representation for classical. And now, either you ignore the next page and just keep in mind that there is a way, but if you're really interested how this in detail goes, then this is explained in the next page. Okay, so let me maybe open until here. So first, you look at ZQ plus minus, so the Laurent polynomial ring over the integers. And for certain pi, so not for every pi, there exists an A form. So what does it mean in A form? In A form, for that, you need first an A algebra, so this U of A, and you need a representation for this algebra, let me call it VA of pi, such that you can realize this algebra as a tensor product. Well, this is not so difficult. And also you can realize the representation as a tensor product and the tensor product over this ring A. So let's assume that pi is given so that these isomorphisms are there. So pi admits an A form. And then you can define the classical limit. Well, the classical limit is just ignore the CQ and just replace it by C. And the C is an A module where Q acts as 1. Well, so for example, if you have a Q over here, and then you can just put it on the other side of the tensor, and then since Q acts as 1, Q is equal to 1 on the other side. Okay, so this is the classical limit. And now, what do you do to go to the graded limit? So the graded limit is, well, there is an isomorphism. As I said, t goes to t inverse. Now, instead of acting with x tensor t, you act with x tensor t minus 1. So you just shift it by minus 1. Okay, so this is now the representation L of pi, where each element x tensor t acts as x tensor t minus 1. Well, this is the representation, and this representation is this way you can study the prime objects. You can describe this L of pi in certain cases, which was done in a paper in 2015 by Brito, Chari, and Mura. Namely, let VQ of pi, a prime irreducible object in that category. So you perfectly now know how pi looks like. So pi has a particular form. It depends on a quiver. Then this graded limit is a cyclic representation, and it has certain defining relations. Well, these defining relations, first everything in plus kills it. Everything with H tensor, a proper T power kills it. And then you take the usual defining relations of the irreducible object. So these defining relations are exactly the defining relations of the local while module, plus one additional truncated relation, which depends on the sinks and sources of the quiver. So if we fix the sinks and sources, say I1 up to Ik, then this matrix Xij, ij plus 1 tensor T on Vx by 0. Okay, so now if you know, if you recognize this module, then you will see that it's a prime level 2 de Mazur module. But I want to emphasize that the highest weight, although it's level 2, 2 de Mazur module, the highest weight is not divisible by 2. So it's really a prime object, which means that it's an indecomposable object. You cannot write it in any tensor product, and it's not irreducible. Okay, and the other thing I want to mention is that it's a truncation by a local while module. So truncation just means all relations are of that form X tensor T to some power. I want to explain it in a minute in more detail. And also the question is, what is the Schur expansion of this module? Or what is the character? Well, you can use the de Mazur character formula in principle to theoretically to calculate it. But what is the Schur expansion? And for that, for the rest of the talk, I want to introduce arbitrary truncated modules, where this is just a special case, and discuss how one can solve this Schur expansion problem of these modules.
Okay. Can I ask a question?
Yeah, sure.
What do you mean by prime de Mazur module?
By prime, I mean they cannot be written as a tensor product of others. So it's like the highest weight in this case is omega I1 plus omega Ik, and it's in level 2.
Okay, thank you.
This is what I mean.
What do you mean by 2? What do you mean by level 2? I mean, how is this? There's no central element here at all. What does level 2 mean?
Yeah, what I mean by level 2 is this. Okay, so first of all, okay, so maybe in this notation, so you take a while group element W and integrable in highest weight lambda. Say lambda is an element in for the affine Kac-Moody in p hat plus. Then the connection between this 2 and this omega I1 up to omega Ik is exactly that if you apply W on lambda, so this extremal weight vector, so the weight of the extremal weight vector is given by, you take the longest while group element, W naught, on this omega I1, so maybe the notation is not the best one, omega Ik, plus 2 times, say, lambda naught. And this you do modulo this imaginary root delta.
Okay, I understand. Thank you. Thank you.
Okay, so this is the connection. Okay, so maybe, as I said, it's maybe a good point to stop, because after that I want to talk about truncated representations. Stop for the question part.
So I have another question. If you suppose I just took the quiver to be start at 1 and just straight arrows all the way to the, then what are the evaluation models that live in this category?
Exactly. So in this case, actually, so the original paper of Hernandez and Leclerc, they considered 2 very particular orientations, namely the one you mentioned, where you just have one direction, and the one which is the sink source orientation. So you just change always the sink source orientation. And in the one you are mentioning, in this case, the prime objects are very easy. These are just the evaluation modules. So this minimal affinizations. So you know in SLM plus 1,
the
you have this,
evaluation modules for the fundamental weights.
Yeah, or 2 times the fundamental weight here. Also.
And what about all the elements? You said it's tensor closed. So what do all the evaluation modules which are in this category?
Oh, that's a good question.
Can I answer Dennis with that?
Yeah, sure.
So if you take the monotonic orientation, so the primes correspond to minimum affinizations, but corresponding to the weight omega I plus omega j specifically. So they are affinizations of this specific kind of weights. So you take all of them, and it's kind of, and then it's well known in the sense how the tensor product is described.
But can one describe all of the objects in terms of pi's? So well, the definition is just take the composition factor and look at them. But can you just say what these objects are in this case?
If you take the tensor product of two objects in that category?
Yeah, for example, if you take tensor products of these kind of representations.
Yes, well, this is done in this paper with Chari. Yeah, we give a complete list of description of the tensor product. Necessary and sufficient conditions to be reducible, and when it's not reducible, we give the composition series of them. But this is for any height function, not only for this monotonic one.
Great, thank you.
Sorry to interrupt you.
Thank you.
So shall I continue, Venkatesh?
Yes, please.
Okay, thanks, Timothy. Okay, so so this part basically motivates to define or to attack somehow this kind of problem for any truncated representation. Okay, so what is a truncated representation? So let me scroll down until the definition. So first, you take a representation for this current algebra, and the reason is clear because we have already clarified that if you take the graded limit, you end up with a representation here. So why not just defining certain classes or families of representations for current algebras? And the families I want to consider here are just truncated representations. And the truncations are basically, well, they depend on the highest weight lambda, of course, because the local Y module depends on the highest weight lambda. And they depend on a certain non-negative integer, which you choose for any positive root, okay? So now this m psi lambda, so this m psi lambda over here, this is defined as, well, you take the same relations as in this Brito-Chari-Mura result. So it's just copied and paste. So this part is the same as this part over here. But with one additional relation, you just replace this 1 over here. You allow here an arbitrary t power, not only 1. So you take xij minus tensor t to some, well, any non-negative integer you allow. So, and this is a family of representations which are basically called the truncated representations for current algebras. And also the remark, which you should see from here, is when you appropriately choose psi ij, well, it's either 1 or big enough, whatever that means, you get exactly the prime objects in this Hernandez-Leclerc category. Okay, so this is generalization of that, but also it includes many other nice families of generalizations. Namely, if you choose psi ij to be constantly equal to n, say it's always the same t power, then this m psi lambda, this conjecturally corresponds to a fusion product. So, but if you don't know what a fusion product is, just think of a graded version of a tensor product, where this lambda 1 up to lambda n has some meaning. And this lambda 1 up to lambda n is the unique n-tuple, okay? The unique n-tuple. Each of these is a dominant integral weight for SLN plus 1. And it's uniquely determined by the property that the product of Schur polynomials is as maximal as possible. So what does that mean, as maximal as possible? It means that whenever you subtract another product of Schur polynomials, it remains Schur positive. Okay, so this is, you can show that to each lambda and n, you can associate a unique lambda 1 up to lambda n, so that this property holds. Okay, And I think we will learn more.
Deniz, I'm sorry, how does lambda enter here?
This lambda enters in the defining relations of the local while. So actually here. So this is, sorry, I haven't explained what this notation is. It's lambda of hi.
Okay, but what is the connection of your lambda 1, lambda n with the lambda?
Oh, sorry. This has no connection at all. So this is, maybe tilde. Sorry, this is tilde, and tilde. And each lambda I tilde is again dominant integral, z plus n. So it's a tuple of dominant integral weights.
Thank you.
So yeah, sorry for that. This lambda 1 tilde up to lambda n tilde you can uniquely associate to this lambda over here and this n, but it's not the lambda of hi from this. Sorry for that. It's not related to it. Yeah. Well, maybe I should
There's one not lambda, that lambda 1 tilde, etc.
Sorry. So yeah, for example, if you take lambda to be 7 omega 1 plus 5 omega 2, so this is now this lambda over here, then lambda 1 is, I think, 3. Sorry, it's 3 omega 1 plus 3 omega 2, and lambda 2 is now 4 omega 1 plus 2 omega 2. So this is, you split the lambda into lambda 1 plus lambda 2. Okay, in a way that this tensor product is as maximal as possible. And well, this basically goes back to conjecture of Chari, Fourier, and Zagaki. Namely, they conjectured that if you take the Schur difference here, so S lambda 1, S lambda 2, minus S mu 1 times S mu 2, it remains Schur positive whenever this condition here is satisfied. And you can show that for this particular choice of lambda 1 tilde up to lambda n tilde, well, it's now 2, that this property is always satisfied for every choice of mu 1 and mu 2. And I think it's still a conjecture. Okay, but I think we will learn more also in just last talk about this. Well, there's also
maybe Deniz, just to interrupt you. So yeah, we formulated this conjecture, but it was formulated before by Lahm, Pylyavsky, and Postnikov. And so we basically recovered the conjecture with a different motivation. But I'm going to explain something on Saturday.
But is it really the same, or is it? I thought it's just some overlap.
No, it's the same. It's for SLN, it's just the same.
Oh, that I wasn't aware. I thought it's just there's some overlap, and this is different in SLN, even in SLN +1.
So this is a conjecture in that same 2007 paper of theirs?
No, it's neither published. So there is a remark in a paper by Dobrovolska and Pylyavsky saying, oh, there's an unpublished paper somewhere, and there's a conjecture, and that's exactly this. And then we started to work on this, and we covered this conjecture. So, but be precise, we have to cite an unpublished paper.
So this is,
but it's not in this original, right?
Say?
It's not in this original Lahm, Postnikov, Pylyavsky.
No, it's not.
Okay. That is what I meant.
And this is referred to in this paper by Galina, Dobrovolska, and
exactly. Yeah.
Okay, so there are definitely okay, so now what I wanted to say, so this is the conjecture of Chari, Fourier, and Zagaki, but there's a stronger conjecture, okay, version of this conjecture, which conjectures generators and relations for V lambda 1 star V lambda 2, okay? So, and this stronger version of the conjecture, this implies the conjecture of Chari, Fourier, and Zagaki, and especially this maximality property of the one which came from the second example discussed above. As far as I know, this is this stronger version is just solved in special cases. For example, when you look at in SLN, when you take lambda 1 and lambda 2 to be a fundamental. And in full generality, as far as I know, it's solved for rank 2. And the consequence is of this result in rank 2 is that you can write in the Schur positivity conjecture of Chari, Fugge, and Zagaki, is that you can describe in the Schur expansion these coefficients by the number of certain lattice points in convex polytopes, which are described by explicit inequalities. Okay, so this is just basically the flavor of what I'm going to do now with the primary reducible objects. I want to do a similar thing where the coefficients are described by lattice points of certain convex polytopes. Okay, so we write this truncation as a direct sum, okay, so into irreducibles. So you can just restrict this module for SLN plus 1, since now the category of finite dimensional SLN plus 1 modules is semi-simple. You can decompose it in this way, and you may ask, is there a way to describe this combinatorially? So this multiplicity, how often an irreducible appears there, or even the graded multiplicity. And then the main tool to attack this is to use the dual functional realization, which goes back to Fagin and Stoyanovsky from '94, but I actually learned this approach from the papers of Adorn and Kedem. And just recently, now we used this functional realization to come up with generators and relations for the fusion product of Krylov-Richteke modules. Okay, so if you go, if you use this functional realization, you can at least describe this space in a functional way. So let me state it in this way. So you take nu to be lambda minus a summation of simple roots, so summation ai alpha I, and then this one, so this multiplicity, is the dimension of a certain vector space. So at the moment, I'm not saying that it's easy to describe this vector space, but let us just first state it in this way. So it's the dimension of the vector space of certain Laurent polynomials. So you allow as many variables as the coefficients of the simple roots. So this ai is exactly this ai over here. And you want these polynomials to be symmetric. So the symmetric group acts in an obvious way on the variables. And these Laurent polynomials are exactly contained here. And then you take the tensor product. And then,
sorry, I forgot what this notation C nu C lambda is.
Yeah, sorry. So this just means the multiplicity. So you take your m psi lambda, so this truncated module, and you ask how often does the irreducible, how often does the irreducible for this highest weight appear in this module? So the Littlewood-Richardson coefficient of this irreducible inside this truncated module.
Great, thank you.
It's the same. It's the same by definition. Okay, so maybe you can also see it here. So from this one, it's the multiplicity. So it's then the dimension of the following vector space. So the first property is just you take all Laurent polynomials, and when you do this evaluation, xi1 equal to xi2 equal to xi plus minus 1, 1, then this polynomial should vanish. The second property is a degree bound. So you want that the polynomials are bounded by this number. So the degree in xi1 is smaller or equal to that. Well, it's enough to require 1 because we know they're symmetric. Okay, so this more or less makes it finite dimensional, this vector space, because we know that these numbers are finite. The third property is if you do the evaluation xi1, xi2 up to xir, then you want that this polynomial is divisible by z to the power lambda I for each I and r. And then the last condition, since also these numbers have to enter, is if you do this evaluation, sorry, there's a z missing here, then this function should be divisible by z to the power minus psi ij. Okay, so there's one thing I want to mention, because it's not easy to come up with a closed formula or with a combinatorial parameterization of the dimension of this functional space. And the reason is the following. So if you ignore this part for a second, the fourth part, then you see, well, this part, it involves the same I. It means it's just a condition on this space. So this is just a condition on this space. The same with the second one. Okay. Okay, the first one is somehow mixing the tensor factors, but in a nice way. But the bad thing is, if you go to the fourth condition, you see you start to mix the tensor factors I plus 1 to j. So this last condition is not a local condition on the symmetric ring. It really involves the whole tensor factor. Okay, it's a property on the whole tensor product, and that's why the force property makes life way harder. But I want to go to it in more detail in a second. Why one needs this force property and what happens if you drop the force property. But before that, I want to say it's also possible to describe the graded decomposition, not only the classical decomposition. The graded character is now just, if you want to count the graded character, you just have to count homogeneous Laurent polynomials. And the degree of the homogeneous Laurent polynomial is exactly given by this. So if you want to calculate the graded piece of this decomposition, you just shift it. Okay, so okay, let me go to this. Let me take another color here. So if I want to calculate this with a p, okay, then all I have to do is I take homogeneous Laurent polynomials of degree minus p minus summation ai plus summation ai plus 1. And if I count this, then I will get the graded decomposition of that. So let me do one example. The example is this, okay? So you take lambda to be 7.5. So if you're more familiar, this is exactly the example I was mentioning, 5 omega 2, okay? So, and this is just 4 omega 1 plus 5 omega 2. And now if you ask how often does this representation appear in this m psi lambda, where this is the lambda and this is the psi ij, you choose it constantly equal to 2, then you figure out there are just two polynomials. Okay, so and exactly these polynomials are given in this way. But you can also calculate the graded decomposition. So what is the graded decomposition? So as I said, the shift is like this. So you take minus p plus, okay, where is it? It's plus, it's here, it's still written here. So minus the AIs, so it's minus 2 minus 1, so minus 3, plus 2 times 1, so 2. So it's minus p minus 1. So this is the homogeneous degree. So now let's look at the homogeneous degree of the first one. So it's minus 4. So this is minus 4 in the first case. And in the second case, it's minus 3. So from here, it follows that p is 2 or 3. So that's exactly why this result comes out, that the multiplicity lives in degree 2 and 3. But generically, to come up with a parametrization, combinatorial parametrization of this dimension, it's hard to describe unless in special cases. Namely, if you drop property 4, you can do that to solve the fusion product of Kirillov-Reshtekin modules, but not the graded one, just the classical one. You can do it also for the graded one, of course, but it was done for the classical one by these two papers, Adon, Kedem, Stone, and Naui. And it's possible to do it for all prime irreducible objects in this Hernandez-Leclerc category, and also for a little wider class, which is now in a work in progress, corresponds conjecturally to minimal affinizations by parts. So what is the theorem? The theorem is first the non-graded one, and then the graded one. So the multiplicity, so this is now again these prime objects in the Hernandez-Leclerc category, C kappa. So this is given by a sum, so it's a positive sum. You sum up over all multi-partitions, okay? So mu is a multi-partition, so you take mu1 as a partition up to mu(n) as a partition, and the number of boxes is exactly ai. And now what is k mu? So k mu is the number of elements, so it's lattice point in a polytope, but the polytope is exactly described by these two inequalities, families of inequalities. So you take points c, d, r, I. Well, I is between 1 and n, it's the rank of SLN plus 1. R is between 1 and AI, and D depends on some number, and this number again depends on the multi-partition. But it's not hard because this number is just you count the number of rows of length R in mu I, right? So for example, if you take this simple one, well, how many rows of length 2 do you have? It's mi2 is 1, and you have also 1 row of length 1, and everything else is 0. Okay. What else is I haven't explained? I haven't explained what is this right-hand side. And this right-hand side is exactly, you take now lambda I, so maybe I should now write lambda of hi, minus some number. And this number is, well, mu I of R is the number of boxes in the first R columns. Right, so you take your Young diagram like this, then you take R and you cut your Young diagram and you count these number of boxes which are left to the R. And this is mu I of R. And then you take these inequalities, and when you count it, how many lattice points are there, you get this multiplicity. And also you can count the graded multiplicity, and the graded multiplicity is a phase of that polytop. And the phase is just given by, well, it's some, again, minus p plus some shift and something which is, well, technically defined on the multi-partition mu. Okay, so just to give you a way how one can use this formula. So let me give you a huge example. So let's take SL9. Okay, so n is 8. And let's take the highest weight omega 2 plus omega 3 plus omega 4 plus omega 5 plus omega 7. And let's take alpha 1 plus 3 alpha 2 plus 4 alpha 3. These are exactly these numbers now. Plus 4 alpha 4 plus 3 alpha 5 plus 2 alpha 6 plus alpha 7 and no alpha 8. So first of all, you have to take all multi-partitions which have exactly AI boxes. Okay, so what is a multi-partition with AI boxes? So for example, this one. So this has 1 box, it's this number. This has 3 boxes, it's this number. This third one has 4 boxes, and so on. And then you can show, when you write down all the inequalities, then you can show that K mu, that this polytop is empty unless for these two multi-partitions. And in this case, you can again show that that the inequalities are exactly given in this way. So for example, you take C1 to 5 less or equal to 1. Well, you can choose it 0 or you can choose it 1. And here you take all points, well, and all of them have to be equal to 1. And now if you write this down, then you can say the multiplicity is 3, and 2 of them appear in degree 4, and 1 of them appears in degree 5. Okay, so but this theorem is nothing special for these weights over here. You can actually take any lambda as long as you keep the truncated relations at tensor 1. So the same theorem works for any lambda. Keep just the same truncations. Okay, I think it's a good point to stop here. Thank you for your attention.
Thank you, Dennis. Are there any questions?
Ask a question?
Yes, please, actually.
So is there some formula for the dimension of those truncated modules?
Yeah, that is something what we are now working on to figure out what happens, especially when you choose all of these psi ij's to be equal to n. But as you probably know, this question you are asking is somehow related to asking for formulas for the Littlewood-Richardson inside a tensor product, right? So because this, how I say? So this, since this module conjecturally corresponds to this tensor product over here, the question you are asking is basically in this case whether there is a formula for the multiplicity of an irreducible in that tensor product, which I don't think is so easy to determine.
But no, actually, I wonder if there is a formula for the total dimension. So for
okay.
just for dimension of the module.
For the total dimension, that I haven't thought about. Yeah.
So you are saying that there is this fusion product formula, yeah, but so I wonder if starting from lambda and the number n, one can give some dimension formula.
Yeah, that I haven't thought about. Yeah, I don't know. Yeah.
And actually, may I ask one more question? So, well, you have this lambda, and is there some kind of connection between the modules corresponding to lambda, mu, and lambda plus mu? So I mean, so suppose you sum up two weights, and is there some connection between the module corresponding to lambda plus mu and the module corresponding to lambda and to mu, assuming that this capital N is fixed?
So you would like to see some kind of tensor product embedding, something like this?
Right.
You're asking for? Yeah, but I don't know. Yeah, I haven't thought about it. Yeah, but it would be nice to see whether somehow it embeds in a way, or if it does not, how it is. Yeah, I understand. Yeah, that I have thought.
So this dropping that fourth condition in your that dual realization, does it correspond to anything?
Yeah, this is just local Y module.
So that is okay. That is just local.
Yeah, and dropping property 4 means dropping this condition here.
I'm just wondering, like, so if you include like some other elementary relations, so the truncated one is understood. For example,
but
fusion of all Kirillov-Reskin understood. Suppose if I take that with one more, let's say, evaluation of irreducible.
Yeah, so you can actually generically say you can apply this dual functional realization thing in basically in two cases. So one is when all relations come from simples. So for example, if you take the fusion product of Kirillov-Reshetekin, then in the ideal, you have just simple ones, right? So all relations come from SL2. Then you can just do it, and then you do not have this force condition over here. So this is basically saying, so well, if you keep the same I, then it means it comes from SL2 relations. If you don't keep it, then the ideal has more relations. And then for the truncated ones, it was possible, but if you go too higher, then it's not easy to describe the functions. Well, you have this dual functional realization, then you have to describe the U minus structure of this module, and this is even not known to me. But once you have this, then you have to figure out the functions which vanish on this ideal, and this is not an easy task if you first of all don't know the U minus structure, and also if you have more complicated relations. So this is the main ingredient here is take m psi lambda. So this is definitely u n minus t on this v, and then this is isomorphic to u n minus t modulo some ideal to describe this idea. So this is this. Yeah. And even for fusion product of Kirillov-Reshetekin, this un minus module was well, I talked a bit to Naoi about this, and he said he doesn't know what the U minus structure is of this. And this is more or less the key ingredient to come up with this theorem. But this is just, again, a very formal way of describing what this Richardson coefficient is. But more explicit, well, I think if you take 2, then it's also possible. But the idea to go to this theorem here, one has to reformulate these conditions in an ideal theoretic way. Then one has to somehow see what the conditions are. And this is again, if you go outside truncated relations, it's hard.
Are there any other questions?
Am I allowed to ask one more?
Yes, please.
So I wonder if there is a connection of these truncated modules with the while modules for the truncated current algebra? I mean, G tensor C of t modulo t to the n.
Yeah. Yeah. So if I understand your question correctly, you take your truncated module, and
no,
then
yes.
just
So
okay.
just,
So
I want to take the truncated current Lie algebra. So this is the tensor product of G with the polynomial algebra modulo t to the n. And then I consider while module for this algebra.
Do you mean just take the normal local while module, modulo t power n? Yeah, it's
No.
exactly, yeah, it's in this class, yeah.
Oh. You are, so I mean the local while module for this truncated algebra, is it the same what you said?
I think so, right? So what is local while module? Somehow it's the maximal indecomposable, right? So if you take the truncated current algebra, then you better take the maximal indecomposable for the usual current, but at least you have to plug in the relation G tensor Tn to get a module for the current. So I think they're the same.
I think you can quotient out the submodule generated by G times t to the n, acting on the entire module. If you quotient it out, this is actually your truncated local while module, and this is what Dennis said before, that this unique maximal element. So in Dennis, when you had this decomposition of lambda into lambda 1 up to lambda n, there's a unique maximal element. And this, then the conjecture is that the fusion product of this one here, there's a unique maximal decomposition, where this tensor product is maximal, and that this fusion product is then the truncated local while module.
Okay.
Yeah, but unfortunately, I mean, this is like. So yeah, in a few cases, I think Dennis computed a few of these, but in general, this is like, no chance, so far.
Yeah,
Dennis, I mean, you computed a few cases.
For example, if all of them are equal, for example, this is one case where it has been computed. And so this was also one hope when I saw this this theorem over here to solve this conjecture Gislam was talking about, that this truncated while module is the fusion of the irreducibles, because you know somehow, well, it gives you the multiplicity, but it's not explicit. That's the problem. It's it's a dimension of a vector space, and you all know it can be a hard vector space to come up with. But at least in this one prime module prime case, in this HL category, it was possible.
Any more questions? If not, I just had one thing. You had this computation done in the paper with Leon Barth. You show it as the vertices. You compute the highest weight vectors at vertices of some polytopes. All right. So how do you actually come up with those polytope points? It was.
This is we probably made also more clear in just last talk, because it's the Gröbner basis approach. So you write down. So first of all, this fusion product of two. Okay, you can show it's a module for say u of g times u of g tensor t. Okay, whatever this means. Okay, so times a cyclic vector. And then what you do is you do Gröbner theory for this part to come up with a highest weight element. So instead of base elements, you get highest weight elements, and then you can index them by these polytopes, more or less. And then these polytopes thing is somehow, okay, how do you get it? So for example, if you take here an arbitrary element, say you take x tensor t, to some power, say n on v, and if you want this to be 0, okay? And this somehow is 0 if and only if this n violates these inequalities of that polytope somehow.
Okay.
So you don't want this point when one of the inequalities is violated. So this is the rough idea.
Okay, thank you. Okay, if there are no more questions, let's thank the speaker.
Thank you. And, yeah, I also want to